This lecture will be very important in expanding your knowledge of the language of mathematics. Today, I will introduce you to several famous infinite sets. They are so commonly referenced that mathematicians have given them standardized symbols. The symbols are often simplified to another standardized form when written by hand. The language of mathematics can have its quirk, but I hope to help you become more conversational in the amazing language of mathematics. The first famous infinite set that I will cover will be the basis for constructing all the other famous infinite sets. This set is referred to as the natural numbers, and they are the natural counting numbers, such as 1, 2, 3. They are the numbers that humans typically use to just simply count objects. The whole numbers, well, they're effectively the natural numbers, except that we're also going to add the number 0 to the set. This is important in abstract algebra because 0 is the additive identity. Anytime you add 0 to a number, you simply get that number back. Additive identity is a very important element in abstract mathematics. So this is why the whole numbers are an important famous infinite set. The integers, they're our next famous infinite set. The integers extend the whole numbers by including the negative values. They represent the wholes along with their additive inverses. The set of integers is one of the most commonly referenced sets in mathematics. You will see the symbol Z, that calligraphical Z that you see there, it will be used very often. The rational numbers, they're our next set to consider. They are effectively the ratios of integers. We define them as fractions A over B such that A and B are integers and B is not 0. Rational numbers, they're the numbers that have decimal representations that either terminate, such as 1 over 4 equals 0.25, or they form a fixed repeating pattern, such as 1/3, 0.333 repeating. Also, all integers are rationals since they can be represented as a number over 1. Now, when we were younger, we might have had a teacher that tells us, oh, a rational number, that will have a decimal representation that forms a pattern. That's not quite true. There are some numbers that are rational that form very obvious patterns in their decimal representations, but that does not mean that they are rational numbers. So to be a rational number, the representation will either terminate or form a fixed repeating pattern. In general, mathematicians do not like using the decimal representation. We prefer to use the fractional representation of two integers. The irrational numbers, they are our next famous infinite set. They include values like pi, the square root of 2, and e. Their decimal representations never form a fixed length repeating pattern or terminate. They cannot be expressed as a ratio of integers. The irrational numbers are an uncountably infinite set, meaning they are far more denser than the set of rationals. Now, the best way I think to represent the irrational numbers is to just basically talk about their definition. Their definition are all the numbers that are not rational. So this lends itself to a complement notation. So a very common way to represent the irrationals is to take the rational symbol and add the complement notation to it. Every number is either rational or irrational, so to define the irrational numbers, all we have to do is define the rational numbers, and any number that does not fit that definition simply becomes an irrational number. In a previous lecture, you may recall that I said, never consider a complement until you've established a domain. Otherwise, it makes no sense for the complement to even be discussed. Okay, well in the previous slide, it appears that I may have forgot my own advice. So in the previous slide, I referred to the irrationals as the complement to the rationals. In other words, the irrational numbers are simply the numbers that are not rational, and I appeal to the complement notation for their symbol. Okay, well at this point, I would like to define the domain. The real numbers are the domain that I'm referring to whenever we split a set of numbers between rationals and irrationals, or rationals and the complement. In set notation, this means the reals is effectively the rationals union the irrationals. They form the continuous number line that you're sometimes exposed to from early childhood. Because they include the irrationals, the reals are also an uncountably infinite set. The real number symbol is used very commonly in mathematics. It's among one of the most commonly used symbols in mathematics, and in research involving calculus, differential equations, or any other real analysis, you'll see the real number symbol labeled everywhere. Moving up the chain of famous infinite sets, we're going to extend the real numbers to create the complex numbers. These numbers are introducing the imaginary unit I. The complex numbers are the numbers having the form a plus bi, where a and b are real numbers. Complex numbers are the foundation for advanced algebra and analysis. And since they contain the reals, they too are uncountably infinite. It's important that you're familiar with the complex numbers because there are some problems in analysis that require complex analysis to even have a solution. Recall earlier in this lecture that I said the natural numbers will be the basis for creating all the other famous infinite sets. What I would like to do with these examples is to show why that's true. So let's start with the set of natural numbers. Now, this is going to start with a discussion about this symbol that I'm drawing. Notice that on the slideshow, I had a very kind of calligraphical, maybe if you've ever played around with fonts on Microsoft Word, the Gothic font, whatever, this would take way too long to write, and it would take way too much time to do it, given how many times these famous infinite sets are written. So in this notebook, show you how these famous infinite sets have a related but somewhat different symbol whenever mathematicians are writing on a board or on a notebook. So I won't be bothered with writing all the other ones. I will just basically write down the handwritten form of these famous infinite set symbols. So recall the natural numbers, they were the set of numbers 1, 2, 3, ... Now obviously this is a countable set because it is the basis for all countable sets. Countable means the natural counting numbers, so obviously this is a countable set. This is the set of numbers 0, 1, 2, 3, ... Now again, this is another infinite set, but it's also countable. And when we say a set is countable, that means that we can represent it using set builder form, where the iterator is this set of natural numbers. So how do I create this set? Well, the set of whole numbers in set builder notation is effectively the numbers having the form x minus 1, such that x is in the set of natural numbers. The whole numbers are effectively a countable infinite set. Now, as a reminder, this is also the reason why we never compare two infinite sets that are countable in size. They have the same number of elements as far as being a bijective map, meaning one-to-one and onto between the natural numbers, because the whole numbers are created by iterating over the naturals. Our next set is the set of integers. The set of integers is effectively the whole numbers with their negatives. So in roster form, we could write ... -3, -2, -1, 0, 1, 2, 3, ... And notice that the ... goes to infinity in both directions, the negative and the positive. So this is a countable set, but remember, we have to use some sort of set builder notation that relies on the natural numbers. Well, we're going to modify that just a bit, and we're going to take some logical leaps that you guys need to be aware of. The set of integers can be constructed in this fashion. You may say to yourself, well, he said there had to be a natural connection to the natural numbers, but here I'm referencing the whole numbers. Here's where we talk about taking simple notions and extending them to create more complex notions. Anytime that you're using an iterator that is a countable set, you're effectively creating another countable set. Since the whole numbers is a countable set, iterating over the countable set of whole numbers means that the integers is a countable set. Even though I've added 0 in there twice, it still will only be in there once in this set builder notation. So even though plus or minus 0 may be two different zeros being added, in the actual set there's only one being added, because duplicates, when you add a duplicate, it's kind of what we refer to as an idempotent operation, meaning you can repeat it, but after you do it once, repeating the operation has no impact. Following through our chain of famous infinite sets, we now have what we refer to as the rational numbers. And the rational numbers, they are the set of numbers of the form a over b, such that a and b are integers and b is not 0. Okay, well, how do we know that this is a countable set? Because it is. Remember what we said, anytime that you use set builder notation, and your incrementer is actually going over a countable set, what you are creating is another countable set. Now, if you want to have kind of maybe a way of counting this, this may actually be more confusing than it's worth, but I'll show it to you just in case you're curious. So we could take the set of numbers 1 over 1, 1 over 2, 1 over 3, 1 over 4, dot, dot, dot. Notice that the denominators are incrementing and the denominators are staying fixed. Then we could do 2 over 1, 2 over 2, 2 over 3, 2 over 4, and notice that the denominators are incrementing, but the numerator has incremented by 1 to be a fixed 2 for all those. And then notice that I could do dot, dot, dot this way for all of these columns, which means the numerator will be incrementing as the denominator stays fixed in the columns. Okay, well then imagine that I'm going to do the plus or minus for each one of these values because it has to be both positive and negative for each and every one of these. So I don't get all cluttered up. What I'm going to do is I'm going to basically say, think of this grid to where I'm going to have dots that represent these plus or minus values, and I'm going to do dot, dot, dot there. Actually, maybe I'll do circles. So I'll do circles for each one of these values, and then dot, dot, dot that way. And then circle, 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 and we keep populating these, and what these circles represent are these fractions to the right that I'm just writing to kind of give a placeholder for them so we don't get all these values kind of jumbled together. Now notice how I can count through these irrational numbers. Each circle represents a plus and a minus. So using my blue marker, I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Notice that I would iterate through all those fractions of integers, positive and negative, by simply working through this grid along the diagonals. So effectively, I'm showing you that I could enumerate in a sequence all the rational numbers as countable numbers in some sort of sequence. I could label them 1, 2, 3, 4, 5, 6 using this construction. So that is just kind of a quick overview of all the ways that you could prove or demonstrate or make a solid argument for why the rationals are a countable set. Probably the easiest and most concise one is to just build up from the logic. Since A and B are iterating over a countable set, the integers, then we know that the set of rationals must be countable. Okay, now we move on to the irrational numbers. Now the irrational numbers, they would be kind of difficult to define by themselves because they're numbers like pi, e, square root of 2. All of these are what we refer to as irrational numbers. Now, the rational numbers are a countable set. The irrational numbers are an uncountable infinite set, which means that they are so dense that we can never enumerate them in a sequence and map that sequence to the set of natural numbers. Also, these are the set of numbers that do not form, their decimal representations do not form a repeating fixed width pattern or terminate. So that's really unfortunate. That would be very, very difficult to describe, except that it's actually very easy. Given that the rational numbers are so easy to describe, and we're saying that the irrational numbers are simply the set of numbers that are not rational, that means we could define them as the ones not being rational. So my favorite notation for the irrational numbers is this. It's the rational number with the complement notation. It looks like I may have kind of violated what I'm claiming about complements of a set, as I mentioned in my slideshow. So I'm going to say the set of real numbers is going to be the domain for the values that we have described so far. So this will be the set of rationals union the set of irrationals. So I've got kind of a circular argument. What I want to tell you is that there are a lot of brilliant mathematicians that work in category theory and abstract mathematics who have went kind of in a deep dive to define all these things in a more kind of concrete, non-circular fashion. The only problem is those arguments may go a little bit out of scope for our course at the moment. So if it's okay, I'd like for you to just say the set of real numbers, rationals union the irrationals. Okay, and finally, our last famous infinite set, we're going to use the reals to extend those and then create the set of complex numbers. So complex numbers, x squared plus 1 equals 0 has no solution whenever we restrict the set of values x to be in the set of real numbers. You learn that there actually is a value that will satisfy this because we refer to it as the imaginary unit. So x could be equal to plus or minus the imaginary unit. Okay, well, the imaginary unit lives in the set of complex numbers. So the set of complex numbers, remember, we have real numbers and we have imaginary numbers, and then when we combine them, we end up with a set of complex numbers. They are the numbers having the form a plus bi, such that a and b are real numbers. So we have a real part, and then we have an imaginary part for the complex numbers. So is the number 4 in the set of complex numbers? Yes, because 4 is equal to 4 plus 0i. Whenever the imaginary part is 0, well, it just cancels out and we could just effectively remove it. So there we have it. We have the set of complex numbers, and that is the broadest famous infinite set that I am going to cover. Pi, Euler's constant, and the square root of 2 are all elements in the set of irrational numbers. So that means that they cannot be represented as a fraction of two integers. We know that the rationals are a countable set and the irrationals are an uncountable set, meaning the irrationals are much more denser. So that means that not only do they exist, irrational numbers, but the vast majority of numbers are irrational. There are some numbers where it's not known whether they are rational or irrational, and you could go online and look it up, and you could find all sorts of examples of where there's famous problems or famous numbers in physics or mathematics to where it's not even known if the values are rational or irrational. We just know that the vast majority of them are irrational. I'll give you an example of what I'm talking about. Even the value pi plus e is not known to be rational or irrational. So we do have the sum of two irrationals becoming rational, even though this is degenerate. There are some other cases where you can add two rationals and you can construct them and get a rational number. I would like to show that the square root of 2 is in fact an irrational number. So the proof kind of goes along like this. We are going to assume to the contrary that the square root of 2 is actually a rational number. Now what this means is that when we go through this proof, we're going to arrive at a contradiction. But the only assumption that I will make is that the square root of 2 is in fact a rational number, and that's going to lead to a contradiction. Once we get a contradiction, that means the statement's false. The only assumption I made was that the square root of 2 is rational, and so that will effectively prove the square root of 2 is an irrational number. So let's get started. So if I'm making the assumption the square root of 2 is a rational number, that means that I could use that assumption and say, well, the square root of 2 must be equal to a over b such that a and b are integers and b is not 0. Now, here we're going to make a little bit of a logical leap that maybe you'll just have to trust me on being valid, but I don't think it requires that much faith in me to believe that it's true. If we have a fraction of two integers, then what I could say is, without loss of generality, and that's typically how mathematicians will write it, without loss of generality, which means that we're making an assumption that is not really an assumption, it's just kind of natural that we would say it, we're going to say that a over b is a fully simplified fraction. Because after all fractions of two integers, they will all have a reduced form, correct? So if all fractions of two integers can be in reduced form, we might as well assume that we're in reduced form. All right? So the square root of 2 is equal to a over b, as we said. Now what I'm going to do is I'm going to square both sides. I'm going to square both sides, and this will give us effectively this. Squaring a square root gives us 2. A over b squared gives us a squared over b squared. All right. Now we're going to start getting in the nuts and bolts and things here. Since this is equal to 2, I can do some arithmetic that's completely valid. 2 b squared must be equal to a squared. All right. Recall what an even number is. An even number is just an integer that's been multiplied by 2. So an even number is a multiple of 2. Notice that it must be the case that a squared is even. Why? B is an integer, b squared is an integer, b squared times 2 must be an even number, so a squared is an even number. Now here's what we have to consider. Notice that a squared is a times a. If a times a, if a were an odd number, a times a would be another odd number, like 3 times 3 is 9, odd. The product of two odd numbers is another odd number. The product of two even numbers is an even number. Now, we cannot mix and match this multiplication because a squared means that a is being multiplied to itself. So either a is an even or a is an odd, and then you're multiplying itself. So what we could say is since a squared is even, it must be the case that a is even. Okay, so a is an even number. Now we're going to take this a little bit further. Given that a is an even number, doesn't that mean that a is equal to 2 times k for some k in the set of integers? Okay, so we don't know what a is. We're keeping it ambiguous, that way this is a general proof. But what we can say is that since a is even, that means that a is the product of 2 and some other integer. Okay, but let's go back. We're not talking about a, we're actually talking about a squared now. So that means that a squared is equal to 2k squared, and that is equal to 4k squared. Okay, so rewriting this, here's what we have. We have 2b squared is actually equal to 4k squared for some k in the integers. Okay, well notice what happens when I divide both sides by 2. I get b squared is equal to 2k squared for some k in the integers. Okay, well, you know what? We've already been through this logic, so this must mean that what? B squared, since it's 2 times some integer, b squared is an even number. Well, that means that b, by the logic we had earlier, b is an even number. Okay, so by this construction and given our assumption, we know now, to summarize what we got, that the square root of 2 is equal to a over b, where a and b are even integers. So this is something that we can logically claim. If our assumption, so let me scroll back through, I don't mean to make everybody dizzy with this, but since our assumption was this, and there has been no other assumption made, only thing we've done so far is just rely on straight arithmetic. That's the only assumption. So given that this assumption was made, we now have arrived at the point where we know that the square root of 2 is equal to a over b, and it must be the case, since we've shown this, that a and b are even integers. But what did we say? We made a comment up here. Without loss of generality, we said that a over b must be a simplified fraction. So, by the assumption that we made, that was not irrelevant, and that is not invalid, it is completely valid, and it was just for us to make. We have the square root of 2 is equal to a over b, where a and b are even integers. So this means that a would be 2 times k sub 1, b would be 2 times k sub 2, where k1 and k2 subscriptions to show that they're different values, where k1 and k2 are in the set of integers. It means that we have a common factor, but we initially assumed that it would be fully simplified. So how could it be fully simplified, but also be the case that it contains a common factor of 2 in the numerator and the denominator? So a and b is fully simplified, but it's equal to 2k1 divided by 2k2, which means we could simplify this further by removing the 2 out of the numerator and the denominator. What we've arrived at is a contradiction. This is a contradiction. It basically means that we have created a fraction that's fully simplified, but the numerator and denominator share a common factor of 2. Contradiction. Our assumption is wrong. So if our assumption that the square root of 2 is in the set of rationals, if that is incorrect, and we only have one other option, it must be the case that the square root of 2 is in the set of irrationals. And at this point, we will draw a little square box, and what this square box means is that the proof is complete. Sometimes mathematicians will write the abbreviation QED, which is an abbreviation for a Latin phrase that basically means I've shown what was necessary. So we have proven that the square root of 2 is in fact an irrational number by using a technique called proof by contradiction. Okay, that concludes my demonstration on my notebook of the topics that we covered. So to summarize what we learned, the natural numbers, they were the basis for which we created all the other famous infinite sets. They are effectively the natural counting numbers, 1, 2, 3. The wholes, they're the naturals, and then we put a 0 in there with them. The integers, they are effectively the wholes, and their negatives, also known as additive inverses. The rationals, they're the integer ratios. The irrationals are just simply the set of numbers that are not rational, and they are uncountably infinite. Whereas the naturals, wholes, integer, and rationals, they are countably infinite. The reals are effectively the rationals union the irrationals. The complex numbers are the numbers having the form a plus bi, such that a and b are real numbers. So hopefully you understand this chain of subsets that I have listed, as well as the irrational chain of subsets that I have listed. So thank you for watching. I appreciate your attendance on this. I hope that you had fun learning about it. I hope you learned something new. Please leave comments. Let me know what I did right. Let me know what I could do to improve in the future. Please let me know what I could do to help you learn this material better. Thank you for watching, and I will see you around next lecture.